Okay, let me illustrate the function of a set associative cache using a very simple example. So we have a sequence of instructions on the left-hand side, and we have the same 4-bit memory that we have been using in our examples. And we have the cache in the middle. So we are going to assume that this is a write back cache, and we are going to allocate a cache block in the cache when there is a write to an address that is not there. So therefore it's write back and write allocate. So now we have 4 cache lines, and we are going to assume that it is a two-way set associative cache. What that means is each set has 2 cache lines, so they are color coded. So you can see that there are 2 colors for the cache, and each one corresponds to a different cache set. And the way that we're going to identify the cache set for an address is using 1 bit, because we have only 2 cache sets, so we just need 1 bit in the address to figure out which set a particular cache block should go to. So what I have done on the right hand side of the slide is taken the addresses from 0 to 15 and partitioned them into these 3 components. So the block offset is easy to understand. We have 2-byte blocks, so therefore we need only 1 bit. So the last bit is for the block offset. We're not really going to use it much in this example. The next bit is the set index bit. Like I said, we have 2 cache sets, and therefore we need 1 set index bit. And the remaining is going to be a tag. And because it's a 4-bit ISA that we are assuming, we have 2 bits for the tag. Alright, so now let me go ahead and simulate the 6 instructions that we have on the left side and see how this would function. So the initial state is that the cache is empty, so all the valid bits are set to 0. Now I have my first reference to address 1, and address 1 has an index 0, which means I'm going to be accessing the set 0. And I'm going to check the tag. Well, the tag doesn't match, and the valid bit is also not set, so clearly this is a cache miss, and I have to bring in this cache block into the cache, and I would store it. That's exactly what I did. And so we have to also keep track of the LRU now. So in the case of a direct mapped cache, we didn't have to bother with the LRU policy, because for every cache block there was exactly 1 cache line that could store it. So if it was a cache miss and we have to bring that cache line into the cache block, bring that cache block into the cache, then we have to evict whatever that was there before. So there was no choice that the cache has to make. Whereas in the case of a set associative cache, we have several choices depending upon the number of ways. So in the case of a 2-way set associative cache, we have 2 cache blocks within a set, and therefore we could evict either one of them if we need to make space. So we need to now keep track of the LRU bit for this cache. Alright, so now let's go ahead with the next cache access to address 5. So for address 5, my cache index is going to be again 0, which means I'm going to be accessing the same cache set as before. But fortunately, I do have space, so nothing to be evicted. I would simply have to bring in this cache block. So the tag was 145, and that is exactly what we would like. And notice that the valid bits have been set to 1 because they are storing valid data. Now when we try to store to address 7, it maps to the cache set 1. So this is for the first time we are going to use cache set 1, and nothing is there in the cache. And because we are using a write allocate policy, we are going to bring the cache block and store it in the cache. And we have 2 choices. We could have stored it in the second way as well, but we chose to do it in the first one in this example. You notice that we have set the dirty bit to 1. Remember that the dirty bit is used for implementing write back caches, where the stores modify the local cache value, and when the block gets evicted, if the dirty bit is set, then you would write back. So because we just modified that data, we are going to set the dirty bit to 1. Alright, so now let's execute my fourth instruction, which is a store to address 4, which is going to map to my cache set 0. So now I have to compare with 2 tags. So I'm going to compare the tag 01 with the way 0 and as well as way 1. And I discover that I have the tag in my cache, and therefore it is going to be a cache hit. And which means that I know I don't have to evict any block because I already have the cache block that I need. I just need to modify it, and when I do the modification, I would change the dirty bit, because previously I had just loaded it, but now I have stored to this block, and therefore I need to modify the valid bit. So we have had our first hit so far, and recollect why we had a hit to this address. We have never accessed this particular address before, but still it turned out to be a hit, and the reason for that was is 4 and 5 are part of the same cache block. So when we accessed 5, we brought in the address 4 as well, and this is where larger cache blocks help exploit spatial locality. Okay, now I have my instruction that loads from address 0. So address 0 has a block offset of 0, and which we don't really care, but the set index is also 0, so I'm going to access the cache set 0. The tag is 0. I'm going to compare with this tag, and I'll discover that, okay, this is a cache hit, which is great. So this would turn out to be a cache hit as well, and nothing else to be done, because the dirty bit need not be modified, because this is a load that doesn't change the state of the cache block. And then I finally have the load to the address 8, which is also going to map to the cache set 0. It has a tag of value 10, which in binary stands for a decimal value of 2. Now I'm going to compare that to tag 0 and 1. Neither of them matches, so therefore it is a cache miss. So now I have to find a victim, and remember, the way I'm going to find a victim is by using the LRU policy, but that LRU policy is going to be used only within the cache set. And so I've been diligently maintaining the LRU bit for between these two cache lines. And so I know that this is going to be my LRU cache line, so I need to evict it. And so when I evict it, I have to check the dirty bit, and because it is set, I need to write back. So I would have to write back to the memory and bring in this new cache block, and then I would have finished my cache simulation.